Hello, pre-calculus. Welcome back. This is your last assignment of the semester. Woohoo! Okay, so remote learning pretty much ends on a bang with this one. We are going to review everything with limits. So it's quite a hefty assignment. I'm going to give you guys a full week to do it though, so there's not a whole lot of pressure on you guys, but it is going to be a few problems, okay? So, basically limits and continuity. This is May 4th material. What I'm going to do is go through this in several videos. Basically, I took what looks like a prototype of a test for limits and continuity, and I'm just going to roll through that. You guys will be working through what looks like more of a test review material so that you get more exposure to different types of problems. So let's get to it. The first example I wanted to go over was one of these deals where you look at a graph. So I'm just going to have this in my hand and show you guys the graph. So you really need to go to Google Classroom and get this document in front of you as I'm talking about it. All right, here we are. So, letters A through D are all about the limit as x approaches -4, okay? So -4 is happening 1, 2, 3, 4 units right here. It appears to be an asymptote. So I'm just going to go by, I'm just assuming you guys have in front of you the paper. So A, B, C, D. So from the left, the curve is moving towards positive infinity. So you'd say that the limit from the left of -4 is positive infinity. You'd say the same thing from the right of 4. The limit as x approaches -4, is not infinity. You would say that that limit does not exist. All right, it does not converge to a specific point, therefore it doesn't exist. Now, the function at -4, it looks like this, all right? That's where a point occupies that x value. Right here, there's an asymptote, and if there's no like emboldened dot on this x value, then you would say that spot is not defined. So you would say f of -4 is an undefined value. Okay, so that takes care of A through D. The next one is all about -1. So, should I leave this? Let's erase it. You're gone. So, E, F, G, H. What's the limit as x approaches -1 from the left? Well, -1 from the left is going to be at 1, 2, 3, 4 units above the y-axis. By the way, remember, limits are always expressing y values, okay? It's always the y value. So 1, 2, 3, 4 from the left. From the right, it's 5. So if they don't converge to one specified point, you would say that limit, like the asymptote, does not exist. What am I doing? Does not exist. Okay. Now, what is the function at -1? Well, because there's a closed point, a closed circle, just indicating that it exists at -1, 4, that's what f of -1 would be. I, J, K, L. We're talking about x approaching 2 now. I, J, K, L. So 2 is x equals 2 right here. From the left of 2, it equals 1, 2, 3, 4, 5. From the right of 2, it equals 1, 2, 3, 4, 5. So the limit as x approaches 2, 5. What is the function's value at 2? Whoopsie. There is no value for it. It's undefined. Are you noticing that I'm not saying does not exist? The function's value is undefined. Does not exist is talking about a limit's existence. All right, M, N, O, P. We're talking about 4 now. So here's 1, 2, 3, 4. Oh. M, N, O, P. So the limit from the left of 4, x approaches left from the 1, 2, 3, 4. X approaches a y value of 1 from the left, a y value of 1 from the right. So 1 here, 1 there. That means the limit, if the left matches the right, the limit is 1. But this rogue point right here is actually where the function is defined. So the function is defined at 1, 2, 3, 4, comma 1, 2, 3, 4, 5. So it's the function's defined there, but the limit isn't. I'm sorry. The limit is 1. The function's defined at 5. All right, Q and R are talking about endpoint behavior. X approaches negative infinity for Q. X approaches positive infinity for R. So, approaching negative infinity, that means you just follow the curve and see what y value it appears to be approaching as you go forever in that direction. So if I continue to go forever here, it is leveling out at y equals 1, 2 units. There's a horizontal asymptote implied at y equals 2. So you would say 2 is the limit as x approaches infinity, of negative infinity equals positive 2. Now if you're talking positive infinity, that y value is not restricted at all. There's no horizontal asymptote extending forever to the right. Therefore, the limit as x approaches positive infinity in this particular graph is positive infinity. Alrighty, now we're talking about continuity. So make sure you guys discuss removable versus non-removable parts of continuity. So, S. Let's just first determine the spots where we have discontinuous or discontinuities. So it's negative 4. At x equals negative 4, it is discontinuous. It is also, I see a hole in the graph at negative 1, 2, 3. There's definitely a break right here at negative 1. There's another one at 2. Now, I emboldened a dot right there, but that's just a regular normal dot. Just like, hey, there's a dot. It's just encapsulated in the line. That dot does not indicate a break in the graph. That dot is just highlighted. Yeah. So it's not a discontinuity. However, at 1, 2, 3, 4, it is discontinuous. All right, let's double check. 1, 2, 3, 4, 5. Emboldened dot, but not a big deal. It's the same as that. So 1, 2, 3, 4, 5. We got them all. Okay. So let's check removability. Would you say negative 4 is non-removable or removable? Asymptotes are non-removable. How about this point right here? Removable. Basically, if the limit exists at a point, it is a removable discontinuity. And the limit certainly exists right there. The limit from the left is 1, 2, 3, 4, 5. The limit from the right is also 5. That means the limit exists there. It's 5. Negative 1, that is non-removable because of the break right there. There's no way to sort of like reconcile that difference there. It doesn't connect to a certain spot. Non-removable here. 2, that would be removable. And this one, some people get kind of confused by the fact that there's an open hole right here and then a random dot floating over there. That does not change if the limit exists or not there. The limit does exist at 4. If you went back, if you rewind the video and check it out, it did certainly exist there. That means it's a removable discontinuity. Doesn't matter if we put a dot up there or didn't. All right, let's lastly talk about letter T. This is an example we talked about finding the values for which the limit of f of x equals 5. So 1, 2, 3, 4, 5. I'm going to squiggle it just to kind of like, I don't know, highlight it. Now I threw all the tricks at you here. So, hey, you know what? Pause the video. Try this on your own. See if you can get the right answer. All right, unpaused it. Yeah. Here's Here's 1, 2, 3, 4, 5. All right, nothing so far, nothing so far, nothing so far. Does the limit as x approaches negative 1, 2, 3, 4, 5 equal 5? It sure does. So I'm going to start a little bracket here to indicate like, hey, individual values go in this bracket to talk about where the limit actually equals 5. Negative 5 is one of those values. All right, so nothing here, nothing here. Oh, the open hole also creates a limit as x approaches negative 1, 2, 3. See, the limit as x approaches negative 3 is 5. The limit as x approaches negative 5 is 5. These both yield a limit of 5. So this belongs in there too. All right, all right, all right, all right. Uh-oh, we got one of these deals. From here to there, we have something going on. So the limit actually does not exist at negative 1. If you check out letter G, we said the limit doesn't exist. So you wouldn't say that you would include negative 1. What you would do is you'd say, I'm going to put a parenthesis here at x equals negative 1 to say, yeah, from negative 1 all the way to 2, this entire x value distance is going to represent a limit of f of x equaling 5. So it should be included here because the limit from the left of 2 matches the limit from the right of 2. So you'd want to put a bracket here. All these little details are showing up. All right, and now a bunch of you probably really want to say that the limit as x approaches 1, 2, 3, 4 is 5. But we just said on example O, the limit as x approaches 4 was 1, not 5. So don't put 4 down there. Please resist. Okay, so we keep going, keep going, keep going. What about this guy? Right? I mean, I'm just highlighting the dot that is inherently there. The limit from the left matches the limit from the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9. X equals 9 is a legit value for that. All right, nothing more to speak of there. So we're going to close these brackets and be done with the graph part. All right, this is kind of this is a 16-part document, so maybe this would be a good time to just stop here and then start the video as I talk about computing limits 2 through 8.